Hello, here we are in section 3.4, which is where we're going to tackle the mystery of what to do when we have a complex eigenvalue. So up to this point, every eigenvalue that we've run into has been a real number. And of course, if you remember, all those eigenvalues come from these four numbers in our system of two differential equations. That coefficient matrix determines everything about that system that we need to know. And so what we need to do is figure out what is the determinant of the modified coefficient matrix. And if you remember, this thing right here really amounts to this matrix right here. It would be little a minus lambda, b, c, little d minus lambda. So whatever your a, b, c, and d values are, that's what the modified coefficient matrix is. And so the idea is if we can find the determinant of that matrix right there, set it equal to 0, and figure out what lambda values would make that true, that's where eigenvalues come from. And so that means that we're actually solving a characteristic polynomial, a generic characteristic polynomial that's of this form. It'll be a minus lambda times d minus lambda minus the product of those two values, so minus c times b, and saying that must be equal to 0. With a little bit of modification, a little bit of multiplication, we can get that this is equal to ad minus d lambda minus a lambda plus lambda squared minus cb. And so what we're going to do is we're going to identify those terms that have a lambda with them. These guys right here, we're going to factor out a lambda. And then these guys right here, since they have no lambda involved, those are going to be our constant term, kind of collectively. And so with a little bit of modification, we get lambda squared, that's the lambda squared term from right there, minus lambda times, we're factoring out a lambda from here, and I'm just going to factor out a minus lambda to make it easier, and that means it'll be a plus d plus the constant term, and the constant term is ad minus cb. And I'm doing this on purpose to kind of show you that that's the single underlined terms, and this is coming from those double underlined terms. So in general, if we have a method for solving a formula that, or an equation that looks like this, solving it for lambda, we could use it to figure out generically what an eigenvalue would be. And it just so happens, thanks to your Algebra 2 class, probably in high school, way back in time, you learned there is a lovely little trick. And that lovely little trick is what we call the quadratic formula. Quadratic, there we go, I can spell formula. And so if we use the quadratic formula, or modify the quadratic formula for this one, it would be lambda equals, the solution is going to be lambda equals, and then our quote-unquote b term, in this case would be negative b, so it would be a plus d up top, plus or minus the square root of b squared, so it's going to be a plus d squared minus 4 times the a term, which in this case is just a 1, times the c, which is that constant term way back here at the end, ad minus cb. And then all that is over 2 times the a, which is just 1. So looking at this thing, you actually could, if you wanted to, use this when you're faced with any coefficient matrix. If you know a, b, c, and d values, you could plug that into this formula and instantly get your eigenvalues. Now what's nice about this is that it also allows us to see where the complex eigenvalue would come from. The fact that we could have a complex eigenvalue only happens when the thing that's underneath the radical causes problems. And so that thing has a name, of course. And let me see if I can grab a different color here, something slightly different here. I'll stick with my blue theme and say that everything that's underneath the radical inside here has a particular name, and that thing we call the discriminant. not to be confused with the determinant. The discriminant you learned about way back in algebra class, and that's basically the thing under the radical. And whenever that thing under the radical is negative, you'd be trying to take the square root of a negative, which leads us into complex territory. So down here, we're going to make our little a little box, a little rule set for what happens to our discriminant. Well, literally, if this thing is ever greater than 0, or another way of saying it is if this thing right here is bigger than all this stuff over here. So if a plus d squared is greater than -4 times a d minus bc, then we know something is going to happen. If it's greater than, then we know it leads to us having 2 real eigenvalues. And that's what we learned about in section 3.2. Right? What do you do when the thing underneath the radical is positive? Well, you wind up with 2 real eigenvalues. And not only 2, but I'm going to actually add a little bullet here and say that they're distinct. Distinct meaning you'd have plus or minus the same amount here, right? And so 2 distinct eigenvalues. The other possibility is if a plus d squared is exactly equal to -4 times a d minus b c. And if those two things are equal to each other, then you'd have one thing minus the exact same amount. That's going to produce exactly 1 real eigenvalue. And that's going to be an interesting case because it's technically plus or minus the same amount, 0. And so you'd wind up with plus or minus 0. So in a way, you have a double root, right? And so this is what we would call a repeated eigenvalue. And we're going to learn about that in section 3.5. So that's kind of put that off for right now. But the one that we're particularly interested for this section is what happens when that discriminant is in such a way that this first term right here is actually smaller than the second term. And so you're subtracting a larger number from a smaller number. You wind up with, whenever that is less than -4 AD minus BC. That leads you to some interesting territory. We have 2 complex eigenvalues. And this is the providence of 3.4. Now, I make a little note at the bottom of the page saying technically real numbers are complex numbers. They're contained within the complex numbers, but that's not the way we normally talk about them. So when I say 2 complex eigenvalues, I'm being explicit and saying that they're complex with imaginary parts. Right? Because that's really the aspect of this that makes it kind of unusual and unique. So now that we have a sense of what are our possible outcomes, what could possibly happen, we're going to take a look on the next page based on what we know about complex number arithmetic. And for those of you who it's been a while since you've done a little complex number arithmetic, it turns out we can do all of the same operations. Complex number arithmetic looks almost exactly like real number arithmetic. There's only a couple of exceptions. One of them you already know, I'm sure, is that if you have the square root of a negative number, you can write that as the square root of -1 times the square root of the number, which is really just I times the square root of the number, right? And so when you're thinking about square roots of negatives, we factor out the square root of -1 as I right out of the gate. So we'll pick up a little bit about complex number arithmetic. But basically all the same operations apply, which means the same situation must be true. That means that our coefficient matrix times an eigenvector must be equal to the particular eigenvalue times that same eigenvector. That must be true in order for lambda to be an eigenvalue and x1 and y1 to be the eigenvector. So let's take, for example, a situation like this down here. We have our coefficient matrix, and you'll notice these are just real numbers. They're even whole real numbers. That makes it nice and simple. And so if you use our eigenvalues formula from the previous page, we can say, hey, I'll just use my eigenvalues formula, and that was -2 plus -2 inside there. That's the relationship between those two guys. And then plus or minus. And then in the square root, it's going to be, let's see, what was it? I can't remember. Like I can remember it. A plus d squared. Okay, so a plus d squared is going to be -4 squared minus 4 times AD minus BC, I think is what it was. And so that would be, what, 4 plus 9? And then in the bottom, it's just 2. It's always just 2. And with a little bit of arithmetic, we can find out that this is -4 plus or minus. In the bottom, it's 2. And so up here, we've got -4 squared becomes 16, and 16 minus 4 times 13, that gives us a total of -36. And so you might be tempted to go, oh, that's just the square root of, that's just 6. But remember, because it's negative, this is technically -4 plus or minus I times the square root of 36, which is 6. Right? All over 2. And I put the I in front of it just as a habit. I always put the I in front of the number until you know it's a real number with no radical, and then you can throw it at the end. But each one of those terms has a factor of 2, so we can simplify it, and it becomes -2 plus or minus 3i. And so what we have is, this is our eigenvalue. And I should say, it's the eigenvalues, because it's plus or minus. There's 2 of them there. So what we have are 2 complex eigenvalues, just as we would have predicted. One of them is lambda 1 equals -2 plus 3i, and the other one is lambda 2 equals -2 minus 3i. And if you're thinking, wow, they just happen to be very, very similar to each other, they are. They actually have a particular trait. Those two numbers, those two complex numbers, are what we would call complex conjugates. And so that's going to become useful for us later on. But for right now, what the heck does that mean? Well, in the old days, I would have taken my lambda and thrown it into the exponent of an e to the power of to be able to see what's going on. Well, how do we see this? Does it show up in the straight line solution? Well, if we take a look, hop on Maple and take a look at this thing, and we actually do a dE plot, notice I turn them into 2 differential equations. There's the dx dt and there's the dy dt equation. And I just take a look at what the dE plot looks like. You wind up with something that looks like this. And so just looking at it, there's no straight line going on here. As a matter of fact, if you start at any point on the phase plane, it looks like you kind of follow a curve and sort of head around and zoom in, and it looks like all roads sort of lead towards the origin. So it turns out that there are no straight lines visible. Now you'll notice I say none visible, because there might be a straight line solution, just not one that we can see on the plane that is x and y. We might need to imagine what happens if we take a look at that third variable coming up and out of the plane. Remember, time, that time variable is coming up and out. But there's nothing visible. And the other thing that we notice is that the origin appears to be a sink, but also a a spiral center. It seems to be doing double duty. The origin, right there at the middle, seems to be the result. If you kind of follow all these curves sort of head towards the center, they get kind of pulled in as they go. And so if you're looking at any initial condition, if you start an initial condition up here, they kind of head like that. If you start an initial condition over here, they'd head like that. Start an initial condition down here, they'd get pulled in like that. So no matter where you start on this phase plane, it appears that every single solution curve is going to head towards the origin. So what the heck do I do with these eigenvalues? Well, I mean, one thing that we would have done in the past is we would have said maybe one of the solutions, like y1, is a straight line solution number 1. And I'm going to put in quotes straight line solution number 1. Is that equal to something like e to the negative 2 plus 3i times t times some eigenvalue? Is that really a straight line solution system? Is it a particular? And I would imagine you're not going to be too shocked to find out that, in fact, it is a straight line solution. Although we don't really call it a straight line solution, we just call it one of the two particular solutions that we can use, just like we've done in the past, to come up with a general solution. And so the next video, we're going to get into the weeds on how to do that. Oh, and by the way, just for fun, if you do a quick D-solve for this pair of differential equations, do a D-solve for the system, you'll find out that indeed there is a solution, and it doesn't involve something as simple as e to just simple power, and there's no imaginary numbers that appear, but we're going to figure out how to connect what Maple says the solution is with what it really is. So hang on to the next until the next time, and we'll take a look in the next video on how to actually do that analytically.